Introduction. The determination of the internal force system acting at a given section of a beam. Draw a free body diagram that exposes these forces and then compute the forces using equilibrium equations. We will be dealing with summation of forces along y equate to 0, or summation of forces along x, which is also equal to 0, or summation of moment at a certain support or point and equate it to 0. The goal of the beam analysis: determine the shear force V and the bending moment M at every cross section of the beam. So we will be solving the shear force and bending moment at a certain point in the cross section of the beam, and we will determine also the maximum shear force and maximum bending moment. To derive the expressions of V and M in terms of the distance x measured along the beam. By plotting these expressions to scale, obtain the shear force and bending moment diagrams for the beam. The shear force and bending moment diagrams are convenient visual references to the internal forces in a beam. In particular, they identify the maximum values of V and M. Consider a simple beam shown of length L. From point A to point B is a distance L that carries a uniform load of W, which is in Newton per meter. From A to B, we have a uniform load of W throughout its length and is held in equilibrium by reactions R1 and R2. So R1 is at support A, which is a ruler, while R2 is at support B, which is a hinge. So a combination of two supports with a ruler and a hinge is a determinate beam, and we can find the value of R1 and R2 automatically using the summation of forces or the equilibrium equations. Assume that the beam is cut at point C, a distance of x from the left support, which is a distance from A to C is x, and the portion of the beam to the right of C be removed. The portion removed must then be replaced by a vertical shearing force V, this one, which is opposite to direction at 1, with a coupled moment M to hold the left portion of the beam in equilibrium under the action of R1 and Wx. A coupled M is called the resisting moment or moment, and the force V is called the resisting shear or shear. The sign of V and M are taken to be positive if they have the senses indicated above. Task 1. Write shear and moment equations for the beams in the given problem. Let x be the distance measured from left end of the beam. Also, draw shear and moment diagrams specifying values at all chains of loadings or loading positions and at points of zero shear. Neglect the mass of the beam in each problem. So here's the diagram, and at point B, which is the support, we have a reaction and designated as vertical point, and this is RB, while at point D, which is a ruler, and the reaction along Y is RD, and we have also RBX. However, we don't have horizontal forces, so therefore RBX is equal to 0. Then, so summation of moment at B is equal to 0. So we will have the moment at B in order for us to eliminate RB, because we don't have a distance which is equal to 0. So RB times 0 is equal to 0. So summation of moment at B, and we can find the value of reaction RD. First, usually you start from the left, all loads from the left going to the right direction. So 30 kilonewton times the distance from A to B, which is 1 meter, and the direction of the 30 kilonewton is downward, and going to B is in this direction, which is counterclockwise. However, clockwise, the sign is always positive, while the direction is counterclockwise, the direction is always negative. And this point R or A going to B, the direction of 30 kN is counterclockwise, so therefore it is a negative sign. Next, at point B, we have RB. As I've said, we don't have a value of distance which is equal to 0, so RB is eliminated. And next, we go to point C, which is a load 50 kN. And 50 kN, we multiply with the distance from C to B, which is 3 meters. And the direction from C to B, the direction is clockwise direction, and therefore the sign is positive. And the last point, which is D, and we have a reaction D, so RD, and the distance from D to B is 5 meters, so 5 meters, and the sign or the direction, it is counterclockwise, which is negative, and equate to 0. Then sum up. 5 RD we transpose to another side, and it is equal to negative 30 times 1 or negative 30 plus 150 times 3 or 150. And 5 RD is equals to negative 30 plus 150 is 120, and RD is equals to 120 over 5, and it is equivalent to 24 kilonewton. So RD is equal to 24 kilonewton, and after summing up based on moment, we will have the summation of forces along Y and equate it to 0. So all forces upward is positive, all forces downward are negative. So we have the first point, which is 30 kilonewton downward, so negative 30 kilonewton. Point B is positive RB, which is we are going to find the value, and point C, negative 50 kilonewton, and the last point, which is D, positive RD, and the value is 24 kilonewton. So RB, and equate it to 0. So RB is equal to, change the sign of all constants, which is 30 plus 50 minus 24 plus 50 is 80 minus 24 is 56 kilonewton. So therefore the reaction at B is equal to 56 kilonewton. So RD is equal to 24 kilonewton and RB is equals to 56 kilonewton. So we put RB, which is 56 kilonewton, and RD, which is 24 kilonewton. So we will now draw the shear and moment diagram. So this one, we have a grid line for shear, and this is for moment, and the value for this is 0, and another for moment is also 0. First, we will find the shear values from A to D. So the procedure always start from the left. So we have at point A, and the point A, we have a concentrated load of 30 kilonewton, and start from 0, we have 30 kilonewton, which is downward. And if we adjust, this is, for example, this is 30 kilonewton. So this is 30 kilonewton, and because it is downward, it is negative sign. Next, if we have a 30 kilonewton from point A, then we go to point B. But from A to B, we don't have any force or load. So therefore, the value for shear from A to B is the same from point A, which is negative 30 kilonewton, and will produce a horizontal line, and this is also negative 30 kilonewton at point B, which means from A to B the shear value or the shear force value is negative 30 kilonewton. Then at point B we have RB, which is 56 kilonewton, and the direction is upward. From negative 30 we go up 56 kilonewton, so 56 kilonewton minus 30 is equivalent to 26 kilonewton, and the direction is upward, so therefore it is positive. So point or 26 kilonewton, and this is the point, and this is positive 26 kilonewton. From this point up to this point, it should be the total distance or the length. It should be the value of reaction B, which is 56 kilonewton. So 30 plus 26 is also 56 kilonewton. Next, from point C, from B to C, we don't have a uniform load or any load. Therefore, the shear force is the same at point B going to point C, and this is, and we'll have a horizontal line, which means this is also 26 kilonewton at point C. And then at point C we have a concentrated load of 50 kilonewton. Then going downward, so 50 minus 26 is equal to 24 kilonewton. So from 26 going downward, this is negative 50 plus 26, and the value is negative 26 or 24 kilonewton, and this is the point, which is negative 24 kilonewton. Next, and the total length of this one is 26 plus 24 is equal to the force, which is 50 kilonewton. Then from C to D we don't have a value or concentrated load, therefore the shear force is the same from point C up to point D, and we draw a straight line or horizontal line, and this is also negative 24 kilonewton. And then at point D we have a reaction D, which is 24 kilonewton, and it is upward. From negative point 24 we go up 24 kilonewton, so which means 24 kilonewton minus 24, and the value is 0, and this is the point for point D. And so this is the shear values, and we'll make a shaded area for this one. And for shear values we have a maximum value of, for V, which is a shear maximum, the maximum value for shear is negative 30 kilonewton. So we have now the shear values from A to D. Then we'll go to the moment. We can use the shaded area to find the moment values from every point of the beam. So first we will designate every shaded area to area 1, area 2, and area 3. So we will designate this one as area 1, and this one is area 2, and this one is area 3. Then we solve per area using the formula. And area 1 shape is rectangle, and the value for base times height is equivalent to the base, which is the length of the beam from A to B, which is 1 meter. We multiplied by the height of the shear force, which is 30 kilonewton, and it is negative value. So negative 30 kilonewton, and this is 30 kilonewton meter, which is the moment. So area 2 is the rectangular shape from B to C, and the base for area 2 is the length 3 meters, and we multiply by the height of the shear force from B to C, which is 26 kilonewton, and it is positive. So 3 times 26 is equivalent to 78 kilonewton meter, and positive sign. So area 1 is negative, so negative 30 kilonewton meter. And last, area 3, which is rectangular shape, and from C to B, and the base is the distance from C to D, which is 2 meters, and the height is the shear force from C to D, which is 24 kilonewton, and the sign is negative, so negative 24 kilonewton, and it is equal to 2 times 24, it is equivalent to 48 kilonewton meter, and the sign is negative. So we have now compute the areas from A to B, B to C, and C to D, and then we plot from A, which is to the left, going to the right, which is at D, and we need to have a value of 0 at point A and the final value as at point D, and the value is also at 0 point. So we start at A. If we have draw a horizontal line, the next curve or line is the diagonal line, and we have area 1, which is equivalent to negative 30 kilonewton meter, and the value from A to B is negative 30, and we will put negative 30, which is also kilonewton meter. And if we have from A to B a no load, and next should be the horizontal line, the next curve or line is diagonal. So from A, the direction is going to negative 30, which is a straight line or diagonal line. Next, from point B to point C, we have an area 2, which is 78 kilonewton meter, and 78 kilonewton meter is positive with a value of B, which is negative 30. So 78 minus 30 is equivalent to 48 kilonewton meter, and the value for 48 kilonewton meter is at point C. So we have positive, so therefore this is the point, and this is 48 kilonewton meter, and we have no load, horizontal line. The next line or curve is a diagonal from B to C. We connect negative 30, the point at B, to positive 48, which we located the value for at point C, and this is the point at C. We have 48 kilonewton meter, and the last area is area 3, and the area 3 is negative 48 kilonewton. So 48 kilonewton minus 48 is equal to 0, and no load from C to D, horizontal line, and the next line is diagonal, which means 48 kilonewton up to 0. So 48, a straight line diagonal, and we need to close the moment, and we have a value of 0. Shaded area, Okay, so we can now determine the maximum moment for this diagram. So the maximum moment in this diagram is 48 kilonewton meter, which means these are the maximum values for shear. Maximum value for shear is negative 30 kilonewton, and the maximum moment is equal to 48 kilonewton meter. So this is how you graph a shear and moment diagram.
Another example, find the shear and moment of the given beam. So we have a beam from A to C with a uniform load of 10 kilonewton per meter and a concentrated load at point B, which is 80 kilonewton, and a reaction at A or RA and a reaction at C or RC. So now we have a diagram and we identify this first as shear, and we designate is as zero value shear, and the other one is moment, and also zero value. We will get the reaction RA and RC using first the summation of moment, which is, for me, I'll be using at point A to eliminate the value RA, and the remaining unknown is the RC. So summation of moment at A is equal to 0. From A to B, we have a uniform load of 10 kilonewton, and then we will get the resultant. So this is A to B, which is 10 kilonewton per meter, and the resultant is halfway of the length of AB, which is equivalent to 1 meter. And this resultant is equal to the uniform load, 10 kilonewton per meter, multiplied by the length of AB, which is 2 meters, or 2 meters, and it is equivalent to 20 kilonewton. We have also B to C, and from B to C, we have 8 meters length and a uniform load of 10 kilonewton per meter. We get the resultant of BC of the uniform load, and we should designate it like this. And this is equivalent to 10 kilonewton per meter divided by the total length of BC, which is 8 meters, or the resultant of BC is equal to 80 kilonewton. And the distance is also halfway of BC, which is half of 8 meters or 4 meters. From AB, we have a resultant of 20 kilonewton. So 20 kilonewton, then multiplied by the distance from the resultant to A, which is 1 meter, and the direction of the resultant from AB is clockwise direction, so therefore it is positive sign. At point B, we have a concentrated load of 80 kilonewton. So 80 kilonewton, and the distance from B to A is 2 meters. And the direction of 80 kilonewtons is downward, and it is clockwise direction, therefore it is positive sign. Then, from B to C, we have a uniform load, and the resultant is equivalent to 80 kilonewton. So 80 kilonewton multiplied by the distance of the resultant to B, which is 4 meters, and the direction of the resultant of BC, which is a uniform load, is also clockwise direction, so therefore it is a positive sign. At point C, we have a reaction C. So reaction C, RC, and the distance from C to A is 8 plus 2 or 10 meters. So this is 10 meters, and the direction of RC, upward direction, which is counterclockwise, therefore it is negative sign and equal to 0. Simplify. So 20 times 1 is 20 plus 80 times 2 is 160 plus 80 times 6 is equivalent to 480, then minus 10 RC, which is equivalent to 0. Sum up 20 plus 160 plus 480, and the total is 660 minus 10 RC, which is equal to 0. RC is equal to 660 all over 10, or RC is equivalent to 66 kilonewton. So we have reaction RC, which is 66 kilonewton, and the direction is upward direction. Next, after the summation moment, we can use the summation of forces along y and equate it to 0. So all forces along y, we sum up and equate it to 0. So we have Ra, the unknown value. So Ra and the assumed value or direction is upward, therefore it's positive. Then from A to B, we have a uniform load and the resultant is 20 kilonewtons. We add up 20 kilonewton and the direction is downward, therefore it is negative sign. At point B, we have 80 kilonewton. So we have 80 kilonewton and the direction of 80 kilonewton is downward also, so therefore it is a negative sign. Next, from B to C, we have a uniform load of 10 kilonewton per meter, and the resultant is equivalent to 80 kilonewton, and the direction is downward. So this is 80 kilonewton also, and the direction is downward. So sign is negative. And the last point, C, we have RC, and we found the value which is 66 kilonewton, and the direction RC is upward, so therefore it is a positive sign and equate it to 0. So we have RA and change that to 20 plus 80 plus 80 minus 66, and the value for RA, so 20 plus 80 is 100 plus 80 is 180 minus 66, and the value for Ra is equal to 114 kilonewtons. So this is the value for Ra, which is 114 kilonewton and going upward. We put the value here. Ra is equals to 114 kilonewton and Rc is equivalent to 66 kilonewton. We have the reactions value, which Ra is equal to 114 kilonewton and Rc 66 kilonewton. We start at 0 to the left, and from point A, we have a reaction A, which is 114 kilonewton, and it is upward. So the direction is from 0 up to 114. And this is, for example, a 114 based on the graph, and this is RA. Then, from A to B, we have a uniform load, and the resultant is 20 kilonewton, which means downward direction. So we will compute the values of 114 minus 20, or equivalent to 94 kilonewton. The value for 94 kilonewton will be at point B, and it will drop 20, and the value is 94. So this is 94 kilonewton. From the uniform load, which is horizontal, we will connect the points A to B, and we will have a diagonal line. So point A to B, and that's the connection from A to B, which is from 111 or 114 kilonewton to 94 kilonewton. At point B, you have 80 kilonewton and the direction is downward, which means we change or we subtract 94 kilonewton to 80, and the remaining value is 14 kilonewton. And this is the point. So this is 14 kilonewton, which means from 14 to 94, this is the concentrated load of 80 kilonewton. We have a uniform load from B to C, which is 10 kilonewton per meter, and the resultant is 80 kilonewton. We drop again because the direction is downward, and the value is 14 minus the downward direction of 80, which means you have a value of negative 66 kilonewton. And it will be at point C. So the destination is point C, and this is the value for C. And designate this as negative 66 kilonewton. We connect the point from B to C from 14 kilonewton to negative 66. So we form a line. That's it. And at point C, we have a reaction C, which is 66 kilonewton, and negative 66 kilonewton. The RC direction is positive, so upward direction is positive, and 66 kilonewton, and equate to 0. So therefore, our shear diagram closes at 0. We need to shade first here, okay, then the small one, and the big triangle. We need to identify first the area to find the moment. So based on AB, and we have here a trapezoid. So designate this as area 1. And from B up to 0 shear at this point, and designate this as X distance. And also the triangle, the small triangle, designate as area 2. And the big triangle below is area 3. So let's find the value of X using the ratio and proportion. So by using the ratio and proportion, we have here, the transfer here, we have 14 kilonewton, this one, and this is negative 66 kilonewton. So this blue one is the area 2 and area 3, and this will be distance x. Okay, so we will use the ratio and proportion of the small triangle, this one, to the big triangle because they have the same angle. The length here is equal to 8 meters. This one is 8 meters. The ratio and proportion of the small triangle and the big triangle, we have the height, which is 14 for the small triangle over this one, over x, the base, is equal to the big triangle, this one, and the height is the total length of 14 plus, this is 14 plus 66, or total of 80. So this is 80 all over the total length of the big triangle, which is 8 meters, or x is equals to 14 times 8 divided by 80, and x is equal to, so let's check, so 14 times 8 divided by 80 is equivalent to 1.4 meter. So the distance from B at to 0 shear is equal to 1.4 meters. And the remaining distance is 6.6 meters. Okay, so we have solved the value x, which means we can solve now the areas. And first one, we will solve the area 1. And the area 1 is a quadrat, and the area 1 is a trapezoid, which means the formula for trapezoid It is 1/2 of the two bases, so B1 plus B2 times height. And for this case, the two bases are 114 and 94. And the height is the distance 2 meters. So we have 1/2 of the two bases of a trapezoid of area 1, which is 114, plus the other side, which is 94, and multiplied by the height or the distance 2 meters. And then area 1 is solved. 114 plus 94 is equals to 208 divided by 2 times 2, or 208 kilonewton meter. Next, area 2. The area 1 is above, which means positive. So 208 kilonewton meter is a positive moment. Next, area 2, the small triangle. And the formula for triangle is 1/2 of base times height. And 1/2 of the base, which is the distance x, or 1.4 times the height, or the shear force of 14 kilonewton. And the area 2 so 14 times 1.4 divides to 2, and the value is 9.8 kilonewton meter. And the sign is positive because it is above the shear line. Next, area 3. And area 3 is the big triangle below. And we have the same formula, 1/2 of base times height, or 1/2 of the base, which is the distance 6.6 multiplied by the height of the shear of the triangle, which is 66, and equal to 6.6 times 66 divided by 2, or 217.8 kilonewton meter. So now we solve the three areas. Area 1, 208 kilonewton meter. Area 2, 9.8 kilonewton meter. And area 3, 217.8 kilonewton meter. So now we plot, and we start to the left at 0 point, or 0 moment value. So we start, and we have a positive value of area 1, which is 208 kilonewton meter, and the designate is 1, and this is 208 kilonewton meter. Then the shape of the moment at this area, from horizontal, which is a uniform load, to a diagonal, and the next is shape is the curve. And how would you know that it's a concave upward or concave downward? When the shear diagram is increasing, which means positive, the moment diagram is concave upward. When the shear diagram is decreasing, the moment is so. How would you know? How would you know if the curve is concave upward and concave downward? When the shear diagram is increasing, which means going up, the moment diagram is concave upward. When the shear diagram is decreasing, the moment diagram is concave downward. So in this case, the shear is decreasing from A to B. So therefore, the shape or the curve is concave downward. And concave downward is from 0 to 208. And this one, and that's the curve from A to B. Then, at area 2, so area 1, so at this point, we have to put line. Then, we have area 2. And area 2 is positive, which is 9.8 kilonewton meter. So we add up the area 1 plus area 2 to find the moment at this point at 1.4 meter. And 208 plus 1.208 plus 9 point or area, so area 2 or the moment is equal to area 1 plus area 2, which is 208 plus 9.8 or equivalent to 217.8. And this one is the point, and this is 217.8 kilonewton meter. And the direction of the shear is downward from point B up to 1.4 meters, and the shear is decreasing. So therefore, it is also concave downward. Next, at this point up to point C, we have an area 3, which is 217.8, and it is a negative value, so therefore this is 1 is negative. So 217.8 less 217.8 of area 3, and the value is 0. And we connect from point 1.4 meter up to C, and the shear force or the shear values are decreasing, so therefore the shape is concave downward. And this one, and this is concave downward. That's it. And we shade it. And now we can have the maximum shear and maximum moment. So B maximum is the maximum value at shear diagram, which is 114 kilonewton positive. So 114 kilonewton is the maximum shear, while the maximum moment is equal to 217.8 kilonewton meter. So this is 217.8 kilonewton meter.